According to the National Electrical Code, also called NEC, and the Institute of Electrical and Electronics Engineers, also called IEEE, Standard 81, antenna mounting systems must be grounded to protect personnel and equipment from electrical hazards such as lightning strikes. The recommended grounding method for an antenna mounting system with power over Ethernet, also known as PoE, is as follows. Firstly, use shielded Cat5 cable. Shielded Cat5 cable contains an additional copper or aluminum shield that helps to protect the signal from electromagnetic interference, also known as EMI. The shield should be grounded at both ends. Secondly, use shielded plugs. Use shielded RJ45 plugs that connect the shield of the Cat5 cable to the chassis of the equipment, meaning both the radio and the surge suppressor. Thirdly, establish a single-point ground. Connect all grounding conductors, including the Cat5 cable shield, surge suppressor ground, and antenna ground, to a single-point ground at the service entrance or a dedicated grounding electrode. Use an 8 American wire gauge, also called AWG, or larger solid bare copper wire for the grounding conductor. The additional messenger wire and Cat5 cable can be used to provide mechanical support for the cable if it is suspended overhead. However, the messenger wire is not intended for electrical grounding. The surge suppressor should have a dedicated grounding wire that is connected to the single-point ground at the service entrance. Do not connect the surge suppressor ground to the Cat5 cable shield. If the antenna is mounted on a chimney, the chimney should also be grounded separately using a method approved by the local building code. If the equipment is installed in an area where lightning strikes are frequent, consider using lightning protection devices, such as surge suppressors with transient voltage surge suppression, also known as TVSS, ratings. It is always best to consult with a qualified electrician for any electrical work or grounding installations. Grounding is a critical aspect of electrical safety, and proper techniques are essential to prevent electrical shock, fire hazards, and equipment damage. Let's delve deeper into the NEC and IEEE standards: shielded cabling, single-point grounding, and surge protection. The National Electrical Code, or NEC, is a widely adopted standard for electrical installations in the United States. It provides comprehensive guidelines for safe electrical practices, including grounding and bonding requirements. Article 810 of the NEC specifically addresses antenna systems, including those used for radio, television, and satellite communications. Key grounding requirements outlined in the NEC for antenna systems include: firstly, grounding the antenna structure. The metal structure supporting the antenna must be grounded to a grounding electrode system. This helps to dissipate lightning strikes and prevent voltage buildup on the antenna structure. The grounding conductor should be sized appropriately based on the size and height of the antenna. Secondly, grounding the coaxial cable shield. The shield of the coaxial cable connecting the antenna to the receiver or transceiver must be grounded at both ends. This helps to minimize interference and protect the equipment from voltage surges. Thirdly, bonding to other grounded systems. The antenna grounding system must be bonded to other grounded systems in the building, such as the electrical service ground and the metal water piping system. This ensures that all grounded systems are at the same potential, reducing the risk of electrical shock. IEEE Standard 81 provides guidance on grounding and bonding practices for electrical systems in general. While it does not specifically address antenna systems, its principles are applicable to antenna grounding. Key recommendations from IEEE Standard 81 for grounding include: firstly, establishing a low impedance ground. The grounding system should have a low impedance to ensure that fault currents can flow easily to ground. This helps to trip circuit breakers and clear faults quickly. Secondly, minimizing ground loops. Ground loops can create unwanted currents and interference in electrical systems. IEEE Standard 81 recommends minimizing ground loops by using a single-point grounding system. Thirdly, using appropriate grounding conductors. Grounding conductors should be sized appropriately based on the fault current they are expected to carry. Copper conductors are generally preferred for grounding due to their high conductivity. Shielded Cat5 or Cat6 cable is commonly used in Ethernet networks to reduce electromagnetic interference. The shield is typically made of copper or aluminum foil and is wrapped around the twisted pairs of wires inside the cable. The shield helps to block electromagnetic radiation from external sources, such as power lines and radio transmitters. It also helps to prevent electromagnetic radiation from being emitted by the cable itself. The shield and shielded Cat5 or Cat6 cable must be properly grounded to be effective. The grounding should be done at both ends of the cable using shielded RJ45 connectors that are connected to grounded equipment. When grounding shielded Cat5 or Cat6 cable, it is important to follow these best practices. Firstly, use shielded RJ45 connectors. Shielded RJ45 connectors have a metal shell that is connected to the shield of the cable. This provides a low impedance path for the shield to ground. Secondly, ground both ends of the cable. Grounding both ends of the cable helps to minimize ground loops and ensure that the shield is properly grounded. Thirdly, use a single-point grounding system. A single-point grounding system helps to minimize ground loops by connecting all grounds to a single point. This can be achieved by using a ground bus bar or a dedicated grounding electrode. A single-point grounding system is a grounding system in which all grounding conductors are connected to a single point. This point is typically a ground bus bar or a dedicated grounding electrode. The purpose of a single-point grounding system is to minimize ground loops and ensure that all equipment is at the same potential. Ground loops can occur when there are multiple ground paths between equipment. These ground loops can create unwanted currents and interference in electrical systems. A single-point grounding system eliminates ground loops by providing only one path for ground current to flow. The benefits of using a single-point grounding system include: firstly, reduce noise and interference. A single-point grounding system can reduce noise and interference in electrical systems by minimizing ground loops. Secondly, improved safety. A single-point grounding system can improve safety by ensuring that all equipment is at the same potential. This reduces the risk of electrical shock. Thirdly, increased reliability. A single-point grounding system can increase the reliability of electrical systems by reducing the risk of ground faults. When installing a single-point grounding system, it is important to follow these best practices. Firstly, use a ground bus bar or a dedicated grounding electrode. The ground bus bar or grounding electrode should be located in a central location and should be easily accessible. Secondly, connect all grounding conductors to the ground bus bar or grounding electrode. All grounding conductors should be sized appropriately and should be connected securely to the ground bus bar or grounding electrode. Thirdly, minimize the length of grounding conductors. The length of grounding conductors should be minimized to reduce impedance. Surge protection devices are designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, and other events. Surge protection devices work by diverting excess voltage to ground, preventing it from reaching the equipment. There are two main types of surge protection devices, which include: firstly, surge suppressors. Surge suppressors are designed to protect equipment from transient voltage surges. They typically consist of metal oxide varistors, also known as MOV, which are connected in parallel with the equipment. When a voltage surge occurs, the MOV clamp the voltage to a safe level, protecting the equipment. Secondly, lightning arresters. Lightning arresters are designed to protect equipment from direct lightning strikes. They typically consist of a spark gap that is connected between the equipment and ground. When a lightning strike occurs, the spark gap arcs over, diverting the lightning current to ground. When installing surge protection devices, it is important to follow these best practices. Firstly, install surge protection devices at the service entrance. Surge protection devices should be installed at the service entrance to protect the entire electrical system. Secondly, install surge protection devices at the point of use. Surge protection devices should also be installed at the point of use to protect individual pieces of equipment. Thirdly, use surge protection devices with an appropriate surge current rating. The surge current rating of the surge protection device should be high enough to handle the expected surge currents. Electrical grounding is a crucial aspect of electrical safety that aims to provide a safe path for fault currents to flow to ground. This helps to protect people from electrical shock and to prevent damage to equipment. Electrical grounding is achieved by connecting all metal parts of an electrical system to a grounding electrode, such as a ground rod or a metal water pipe. The grounding electrode provides a low impedance path for fault currents to flow to ground. When a fault occurs in an electrical system, the fault current will flow through the grounding conductors to the grounding electrode and then back to the source of power. This causes the circuit breaker or fuse to trip, interrupting the flow of current and preventing electrical shock or equipment damage. There are two main types of electrical grounding systems, which include, firstly, equipment grounding. Equipment grounding is the process of connecting all metal parts of an electrical system to a grounding electrode. This helps to protect people from electrical shock by providing a low impedance path for fault currents to flow to ground. Secondly, system grounding. System grounding is the process of grounding the neutral point of an electrical system. This helps to stabilize the voltage and to prevent overvoltages. When installing an electrical grounding system, it is important to follow these best practices. Firstly, use a grounding electrode that is appropriate for the soil conditions. The grounding electrode should be made of copper or galvanized steel and should be buried deep enough to reach moist soil. Secondly, use grounding conductors that are sized appropriately for the fault current. The grounding conductor should be made of copper or aluminum and should be sized according to the NEC. Thirdly, bond all metal parts of the electrical system to the grounding electrode. This includes metal conduit, metal boxes, and metal equipment enclosures. By understanding and implementing these grounding requirements, you can significantly enhance the safety and reliability of your antenna mounting systems, ensuring the protection of both personnel and equipment from electrical hazards. Always consult with qualified professionals for electrical work to ensure compliance with local codes and regulations.